once you get into that insulating versus conducting, one, I'll have an engine. Oh, it's recording. Yay.
This, I think the TV
Okay.
shows.
So right now we can't see you, but at least it's recording. So that's good. So you want to look at that. Thank you very much, Jay.
What time is this class over?
We're done at 1:20.
Okay.
So when you are working problems, you'll see it and you'll go, okay, E inside a conductor is going to be 0. But if I've got an insulating sphere, I'm going to have a uniform charge density. I'm going to have a variety of things. So we're going to start right now. We're going to have a solid insulating sphere that has a radius of A. We're going to look initially at a point that's outside that radius A. And we're going to calculate the electric field at this point. But we're going to do it differently than we've done it before. Okay, we're going to do it a little differently than we've done it before. We're actually going to use flux and use flux to our advantage in order to get there. So this is going to have a charge density rho, and it's going to have a total charge Q. So I can start out with my equation for flux. And we can use Gauss's law to our advantage. Okay? Gauss's law says that the flux is going to be equal to the charge inside a Gaussian surface. Since we're dealing with something outside of my insulating charge, that's going to be outside, so I want the charge that's inside. So Gauss's law lets me jump right to that. Epsilon, that's my permittivity of free space. Okay? That's my permittivity of free space. So now we know what this integral is over my entire surface. This happens to be a sphere, right? So if I'm integrating over the entire surface of a sphere, I'm looking at the surface area of a sphere. So this is just going to be E 4 pi r squared. Because I have a uniform sphere, and I have my sphere that's going around. My area, if I integrate over the entire area of my sphere, it's going to be 4 pi r squared. And that's going to be Q epsilon. Now we're solving for the electric field. Okay, there's my electric field. It's 1 over 4 pi. I'm going to write it fancy. Okay, I took my 4 pi, moved my epsilon over there, and I get Q over r squared. This should look very familiar. This gives me K, Q over r squared. And because we know the direction, because it's going to be perpendicular to the sphere, we know that this is going to be in the r direction. Which we started back with about a week ago, that the electric field was K, Q over r squared. So what Gauss did is he brought through the mathematics to get what they'd already been observing. And one of the things that we've done is we've shortcutted everything because we happen to know if I have a Gaussian surface and I can approximate it as a sphere, I don't have to do any hairy integration. I can just go straight to my surface of the sphere. Makes life much easier. Okay? Makes life much easier. Now this only works if R is greater than A. That only works if R is greater than A. Now, if I want to do this for a point inside my conducting sphere, well, we know that Q inside is going to be rho times the volume of whatever it is that I'm going to be looking at. And if I do that, we know the volume of a sphere is 4/3 pi r cubed. So if I draw my Gaussian surface, I can still use this right here. Nothing has changed, okay? Nothing has changed except what my Q is. So I'm going to do E is 4 pi r squared. But now I'm going to put in a row 4/3 pi r cubed divided by epsilon. Rearrange it for my electric field, and I get E is equal to rho r 3 epsilon for r less than a. Now that's the actual result, okay? But I don't want to do that. I want to show you some really cool mathematics. I want to show you some really cool stuff. Okay, so we can do for r is less than a, and we've got that conducting sphere there. So let's play with this a little bit more. And what we're going to do is we're going to define rho. Rho is going to be Q divided by 4/3 pi a cubed. Rho is charge per unit volume. Okay, so this is my total charge on the sphere. That's the volume of the sphere. So if I plug that into E, I get Q 4/3 pi a cubed r 3 epsilon. I'm going to move my epsilon over here with the 4 pi. And the 3's cancel each other out. So I end up with 1/4 pi epsilon. And I've got a Q over a cubed, and I have an r. And that's just equal to k, so I can rewrite this as k q a cubed r. And this is for when r is less than a. Now, what's going to happen next is going to be important from a physical standpoint. All right? And we'll even talk about some direct chemistry in this case that makes a huge amount of difference. So if I'm plotting electric field for my sphere versus distance, okay? If I'm plotting electric field on my sphere versus distance, and this is an insulating sphere, and this becomes A, which is the surface of my insulating sphere, my electric field is going to go as a straight line until it gets to the surface. So this is proportional to R. But once I get outside of my surface, the electric field is going to fall off as 1/r squared. And this is an important result. And we can make use of this. And we do make use of this. So let's look at an actual physical system. Okay. I have a surface, and this happens to be, we're going to have this negatively charged. Okay? So we have got, think of this as, we've done that, or we've seen this experiment in chemistry. So I have a plate that's got a negative charge, and I have a plate that's got a positive charge. And my system, when I've got this through here, I've got all my cations and anions floating around in the system. And we know that's going to conduct electricity because we've been told electrolytes conduct electricity. But if I want to do electroplating, or I want to do evolution of hydrogen, or I want to do something, I have to know what's physically happening at the surface. And that electric field falling off as 1 over r squared is going to be important in terms of attracting stuff to the surface. So if I have a lot of positive cations, such as hydrogen protons, the idea of having that charged system is that I'm going to stack up these little hydrogen protons over here until 2 of these join up and come off as a hydrogen molecule and come off as a hydrogen gas. And being able to do that as we play with it, that's electrolysis. It's also electroplating, because I want to get the positive nickel ions onto my surface, or I want to get the positive silver ions onto my surface. So electroplating is going to do the same thing, and this electric field is 1 over r squared is going to drive how those ions go towards the surface. So it's an actual physical property that I want to use and I want to make use of. So we have lots of fun stuff. Now, we all know that I am not particularly fond of electricity, right? My undergraduate research was evolution of hydrogen at the cathode, and studying this actual physical process that was going on and looking at the difference between hydrogen atoms and deuterium atoms and how this 1 over r squared at the cathode actually impacted the overall value of electrolysis. You know, I'm a sucker for punishment. I'm a sucker for punishment. And we talk about uniform electric fields, okay? Uniform electric field. We can measure, and it turns out we will measure it because we will know the voltage and we can actually measure it. I have 2 plates. It has a uniform electric field. I can put positively charged ions in there, and I can actually get them to line up. And they will be actually lined up and form little pearl chains based on the electric field that you have in there, get them to balance, and use it to balance charges just like Millikan balanced charges in the Millikan oil drop experiment. And I could measure, as you guys are about to find out in thermodynamics, okay? Thermodynamics says PV is equal to nRT, right? Ideal gas law. Right? Ideal gas law. What are the assumptions for the ideal gas law?
Z got equal 1.
Huh?
Z equals 1.
Z equals 1, but what does that physically mean?
On a little chart, when I go on the little chart, Z equals 1.
Well, what it physically means is I can disregard the size of the molecule. Number 1, I can disregard the volume of the molecule or the atom. Does not matter. Okay? The volume does not matter. That's disregarding number 1. What else do I disregard? If 2 atoms hit each other, they are not going to interact. They're going to bounce off of each other like billiard balls. Okay? So that's the second thing that I disregard. So the first thing I disregard is the size of the atom or the molecule. The second thing I disregard is that there's any physical interaction between the 2. So ideal gas law works really, really well in the room our size, because I don't care what the size of the particles are, and the odds of something actually interacting with each other in the volume that I've got for the size of my room, not a big deal. Now, if I have a piston, right? If I got my piston, and I have my piston thing in here, and I start compressing can I continue to disregard A, the size of the molecule, and B, whether or not the molecules are going to interact? Nope. I'm forcing them in close proximity to each other. They are going to interact, and now the volume does make a huge difference. So, and when I'm doing that, I put energy into it, which energy is going to help me go over the phase change, and I'm going to probably go from a solid to a liquid or a liquid to a solid, depending on which way I'm pulling the piston. But what you're going to find is we are going to make a correction to that. The two corrections that we make, one is called, it's a van der Waals. I'm sure that's just the alarm test, right?
We should evacuate.
If we should evacuate?
Just in case.
One is related to the interactions, and that's called the van der Waals force. Okay? And that's actually based on my physical interactions between the various items that's there. Van der Waals forces come into play, and the other one is just based on the volume of the particle. And you'll get those initial two corrections along the way. Doing this, if I balance the charges with the electric field, I've balanced the electrostatic force, but the particles are still going to have a gap. And that gap actually is measuring the van der Waals forces. That comes into play with nanoparticles, comes into play with a lot of plastics, comes into play with macromolecules, comes into play with a whole ferrofluids, ferrofluidics, electrical rheological fluids. There's a lot of physical stuff that I got to worry about van der Waals forces. That was my graduate work. That involved electric fields, magnetic fields, optics, and ideal gas law. Or not ideal gas law, as the case may be. So it does have practical implications. And the really cool thing is that can be an optical and or circuit for quantum computing. We actually demonstrated an optical circuit for quantum computing by looking at the forces associated with both the electric field forces, the magnetic field forces, the electromagnetic field forces, and the van der Waals forces associated with particles. So those are fun things that we work with this stuff. So there's actual practical, besides making devices, there's actual practical stuff associated with it. So let's look at a problem here. I'm going to have a sphere in the middle. It's an insulator. There's going to be a gap. Okay, and this outside surface is a conducting shell. All right? And we're given that rho for the insulator is Q 4/3 pi r cubed. And the radius for that is A, so this ends up becoming 3Q 4 pi A cubed. So that's our total charge on the insulated surface. All right? The total charge on the insulated surface. So this is an insulator, this is a conductor. So we want to find the charge at R, I want to do this at R less than A, which we already did. There's the, I can rearrange this and find the charge at R less than A. That's just going to be based on my charge density. We know how that's going to be there. Well, this, I can do my electric field for R less than A. We did it. That's this right here. We've already done it. Now, if that's A and this is B, we want to find the charge for anything that's between A and not quite at B. Okay? So anything that's A, not quite at B, And guess what? It's going to be the charge on the inside. Now, if I want to look at the charge on the inner surface, okay, the inner surface of my conductor, we can look at the charge density, or the charge, it's charge density, but it's the surface charge density. That's going to be my total charge divided by 4 pi r squared. So if I'm looking at the charge on the inner surface, if this is a positive charge, this is going to be a negative charge, and it's going to equal the same, because I'm going to induce a charge on the inside of the surface. I'm going to induce a charge on the inside of the surface. So if this is a positive Q, the charge on the inside of the surface is a negative Q, charge on the outside of the surface is a positive Q. This charge is inducing this charge. This charge induces that charge. The electric field inside here is equal to 0. And then we have a Gaussian surface out there, and we've already figured that my electric field is going to equal whatever my charge is, because it's what's on the inside. So the math isn't necessarily what's going to kill you, although you guys are going to jump straight to the math because you can. You can look at these and infer what's going on by understanding a little bit of what's happening. And the key is picking your Gaussian surface. The key is picking the Gaussian surface. Oh, let me see. So let's just do it this way. Let's write conductors in electrostatic equilibrium, because that's what's going to give us that lovely piece. All right, the key for a conductor to be in electrostatic equilibrium is that there's no net motion of charge. And we're getting ready to start playing with those charges and making those charges move. But for right now, in electrostatic equilibrium, there is no net motion of charge. So when that happens, the electric field is equal to 0 everywhere inside the conductor. And if the conductor is isolated and carries a charge, it will be on the surface. And then the electric field just outside the conductor is surface charge, whatever my surface charge density is, divided by epsilon. And now I'm about to explain lightning rods. Okay? Because one of the things that this ultimately leads us to, and Gauss would explain it nice and peachy dandy. If I have an irregularly shaped conductor, okay? I've got an irregularly shaped conductor. Surface charge is going to be across the top. The charge density here is greatest where my radius of curvature is smallest. Charge density becomes greatest where my radius of curvature becomes smallest. Which means the charge is going to end up concentrating on the sharp points. Which means that if I have a lightning rod, that's where the charge is going to want to go. And since I'm going to build up charge, that's where you're going to get the zot. That's where the zots happen on clouds, is where the cloud formations are going to have the smallest radiuses of curvature. You're going to get to the point that they're going to have the zot. And it's just as common to have ground to cloud lightning as it is to have cloud to ground lightning. And a lot of times, your lightning rod is not being struck by the lightning. Your lightning rod is actually striking the cloud. But the whole idea is the lightning rod is connected to the earth, which is a great big ground, and I don't destroy my house or start a fire or have your tree splinter in a gazillion pieces. I have lived in a house that has been struck by lightning, and I've lived in a house that's had a tree just outside struck by lightning. Not fun. I don't particularly like thunderstorms. Don't particularly like. That one was interesting because when it hit the tree, it shattered the tree into a gazillion toothpicks. It did not catch fire. There is something called cold lightning versus hot lightning, and it's the propensity of whether or not it's going to catch something on fire. And that tree just disintegrated into a lot of little toothpicks. But these are the keys for my conductors in electrostatic equilibrium. Now, of course, we're going to disrupt that equilibrium, and that's how we're going to get current. But if it's an electrostatic equilibrium, we have no electric field inside the object. So that gives us our doing our surfaces, our Gaussian surfaces. Gives us being able to find charge densities, being able to find charge. And I think I'm going to stop there, and we're going to start doing potential. And I did get some of it recorded. Yay! You're getting a quiz. I meant to have it up by now, but this morning got busy.